Hey y'all, we're gonna go through this quiz here. If you watched the video I posted on light, then you already have a decent idea about these answers, but it was a rather long video, so I plan on still teaching in this quiz, but I'll streamline the approach a little bit. In looking at a wave, we're gonna go through and label this stuff. Quite frankly, I think this is a little more juvenile than maybe I'd want it to be, but this is a quiz that was given to last semesters, and I'm trying to be consistent in what we learn. So amplitude is always going to be the height of the wave. So the amplitude would be pretty much from the center to the top. And we'll label that A for amplitude. Wavelength is always going to be the distance between any two repeating points. So pretty much you could choose like from here to here, or from the bottom to the bottom, or the top to the top, which we'll get to those names here in a second. But wavelength is going to again be the distance between here and here, which is how long it takes, or which is the distance it takes to complete a full cycle. So I usually like to go from crest to crest, which brings me to the next thing. A crest is going to be the top part of a peak, and a trough is going to be a bottom part. I can remember that because that's what you call something that, you know, maybe a pig drinks out of a trough and you put water in it and it looks like that, and so it makes sense to me. The direction of the wave, for all light waves, we're always going to be looking at going almost from left to right, just like as if this were an x-axis. So our wave direction will be going this way. Now sometimes you have certain wave propagations that, and you have a z-plane, etc., but this is just a two-dimensional standard wave that you'll come across when we're discussing light. We're not talking about electromagnetic waves specifically. Okay, so the next question is define frequency. Before I get to this, I mean, I can give you a standard definition. Let's talk about what frequency is, because it's easy to just memorize a bunch of equations without ever really thinking through what's happening. So the question is define frequency. Well, let's say we have three different waves. We'll give them all the same amplitude. Amplitude, by the way, doesn't change the energy of something. Amplitude just changes the brightness of something. So wave number one, we'll make it like this. Wave number two, we'll make it like this. And we'll say they have similar amplitudes. I guess they really don't. I'm not very good at this. And wave number three, I should make it a little bit thinner there. Cool. So if we look at these right now, pretty much the only thing we've discussed so far has been amplitude, which again, we'll just say that this is to scale and these all have the same amplitude. They're all the same brightness. We look at the wavelength, so from here to here, from the crest to the crest here, this has a higher wavelength, so this is the highest wavelength. I think you'd agree that's a much bigger space than down here, for example, and I'll take one of these good ones down here, where we have from here to here, and that's a much shorter wavelength. And now let's talk about what frequency means. Well, all of these are going to be traveling at c, which is the speed of light, which is 3.00 times 10 to the 8 meters per second. Okay, and how I like to explain this is, let's say that, let's go ahead and put a boxing glove on the top, on every crest. This might take a while. So I know that's not a good boxing glove, but since when have you ever seen me do good art? Okay, and so I'm gonna give it about one more to make a point. Okay, so now these all have boxing gloves on the top of their crest, and let's give, hold on, Sawyer. Oh, let's make this guy, I don't know why I started drawing him with the top hat. My kids found the arrow to their wolf sword. That's amazing, you guys! Hey guys, I'm filming a video. Okay, so there's this guy, and he's about to be punched. All right, now all these boxing gloves represent essentially him getting punched. So as I go like this, which one do you think you'd rather be punched by? The one right here, which is like boom, boom. The one right here, boom, 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 boom. Or the one down here, boom, 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 boom. Personally, I would not want to be punched by this one. And we're pretending that all the boxing gloves have the same amount of energy essentially hitting you. So again, these travel at the same speed. So watch them again. They're all traveling at the same exact speed. But this one's hitting him a lot more often, right? This is what frequency is. It's hitting him more often in a certain period of time. Boom, 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 boom. Okay, so this has a higher frequency, which we represent with nu. All right, and this hopefully shows you conceptually that wavelength and frequency are actually inversely proportional. This one has a high wavelength, but a low frequency. And this one has a high frequency, but a low wavelength. Okay, so if we understand this, we can understand a lot more over here when we get to, that's the key, there we go, when we get to over here. So it says, define frequency. Well, when we're talking specifically about light waves, frequency is specifically using units, the number of waves that occur per second. How many punches this guy's gonna get in a particular second, going at the speed of light, 3.00 times 10 to the 8th meters per second. Okay, now it says if you double the frequency, you do what to the radiation? Well, we could look at a bunch of equations, and in fact, I will just to prove it that way as well, but conceptually now, we ought to be able to figure out these answers just understanding what we know now. So, if you double the frequency, you do what to the energy? Well, let's say the frequency was doubled between here and here, and it looks like it practically was. Looks like for every two, there's maybe 4 of these. So as you go through, boom, 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 this one's hitting 2 times more because it's got double the frequency. So you double the frequency, you're gonna double the amount of energy. Okay, sorry, I lost you for a second, but I'm back. So it says if you double the frequency, you're going to double the amount of energy, and I told you I'd explain that in terms of an equation as well. So Planck came up with this, his constant, 6.626 times 10 to the negative 34, but the appropriate, or the most important part of the fact is that it's a constant. So he relates energy to frequency using his constant, and essentially that's what the constant does. So and its units are actually joules times seconds, which makes sense because frequency has a unit of inverse seconds, and that's how the seconds cancel out and you're left with units of joules for energy. The question is, what happens if you double the frequency? Well, if you increase this, because this is a constant, you have to increase that by the same amount, and that explains, hopefully, logically, why you would double the energy. All right, so if you double the wavelength, you do what to the energy? Well, let's take a look at our wavelength. It's kind of exactly the opposite question. So here we have a wavelength from here to here. If we double that, from here to here and here to here, what do we do to the energy? Well, it looks to me like we're going to decrease the energy because this one had half the energy that this one did, because this one was getting punched 2 times more. Now I can explain that to you this way through essentially 2 different equations, which is we know that C equals lambda nu. It's a really bad nu. Let me make that a better nu. There you go. So these 2 are inversely proportional, as we discussed earlier. And so if you double the wavelength, if this goes up by 2, this has to go down by 2 to keep this constant, which is 3 times 10 to the 8 meters per second. So now all of a sudden you've decreased this frequency by 2. In other words, you've halved it. So now we can go back to our energy equals h nu and say, hey, if we half this, what has to happen to the energy? Well, it also has to half. So you would half the energy. Now it says if you double the wave number, you do what to the energy? Well, we have to have an understanding of what wave number is. Wave number is very similar to frequency, but it's the number of waves per length, essentially. Usually when you're talking about IR spectroscopy or something to that effect, you're going to be looking at centimeters inverse centimeters. So you're looking at the number of waves per centimeter. Let's go ahead and look at this thing and say, okay, well, if you double the wave number, in other words, let's take a particular length from here to here. Here you only had 2 in that space. Here you've got 4 in that space. Here you've got maybe 8 in that space. So as we went from bigger to bigger wave numbers, what happened to the energy? Well, the energy went up. So you could look at it this way and say that we know it's going to double because these are linear relationships, or we could prove it this way. I could say that wave number actually equals 1 over the wavelength. So if we double the wave number, that goes up times 2. In order for this number to go up, this number has to decrease by 2. Now we've decreased the wavelength. Now we can go over here. Okay, well, let's just add another equation, c equals lambda nu. So we decreased the wavelength. That means, hey, we had to have doubled. If we decrease this by 2, we had to double the frequency. And then we can say, okay, E equals h nu. Well, now we've doubled the wave number, therefore we have to have doubled the energy. So we can go through and do this whole process, or we can just logically think it through, which I really prefer you guys do, because that's where you're actually going to really understand and really learn. All right, y'all, hope that helped. Have a good one. Bye.